Hello, hello everybody. I'm François Boué. This is a pre-recorded talk, unfortunately, because I couldn't come. The title you can read. I said to Chris Garvey it was a little pompous, and Chris told me Anglo-Saxon love pompous. I'm just citing. So I hope the talk will be pleasant for you. Let us now start. So I will start from a very usual and simple object, which is a sphere, actually an assembly of a spherical sphere of different size with a wide size distribution in the dilute regime, so that we see actually only the form factor of these spheres. And this form factor is represented here in a log of I log of Q representation. And you can see that it's composed of two parts, as well known, the Grignon law at low angle, this this plateau regime, where you can obtain the radius of gyration, which corresponds to the global form, and a large Q region with a decay as Q at the power -4, which corresponds to the so-called Porrod law, diffracted by a compact object with a neat interface. One must add that the scattering is isotropic, obviously. As you can see on this scheme of a detector plate, okay, where different circles are traced corresponding to different iso intensity line, different level of intensity. Okay, let us now imagine that we are deforming this collection of spheres with, for all of them, the same deformation ratio, lambda x along the direction x, y along the y, and z along the z. And then we will have a scattering, okay, which you can see on the scheme of the detector on the left-hand side. A scattering which is anisotropic, which is actually composed of ellipsa. And if you look at the scattering in the log of I, log of Q representation, you see that now the scattering is shifted to the right for the perpendicular direction and to the left for the parallel one, which means that we have the same zero Q limit in any direction, and that along the parallel direction we have a larger radius of gyration, which means the intensity is decreasing faster, and at large Q on the same green curve we have a Q minus 4, which corresponds to a lower value than for the isotropic scattering, which is here in red. So in any, for all values of Q, the value of I are smaller in the stretch direction than in the normal one, and the value of the intensity in perpendicular direction is always larger. So until now, we have some scattering which is actually only sensitive to the external shape of the object, since the sphere is not scattering from the inside. We have no information on internal deformation, and everything look as we had a fine deformation with respect to the deformation of the object. Now we will turn on to the polymer chain case, and we will just see now that it is different because the internal deformation of a chain is not the same as its external one. Let us consider a Gaussian chain stretched by its ends. The square distance between two monomers, I and J, has two contributions. In the first one, RAJ squared is proportional to J minus I, as in a usual Gaussian chain non-stretch. The second contribution is proportional to J minus A over N at the squared. That means it corresponds to what you would have for a two monomer along the rod-like chain. So finally, when J minus I is of the order N, the distance is strongly deformed, and when J minus I is very small compared to N, you tend to no deformation. This is what we call a loss of affineness when decreasing the distance. A classical example is the one of a chain in a rubber under equilibrium with deformation. Look at the left-hand side figure. We can imagine on this figure that first all scales are deformed homothetically, in other words, finely to macroscopic deformation. Then chains relaxes, and as shown in the lower drawing of this figure, there is a loss of fineness at all scale smaller than RC, which is the mesh size. To show the effect on the scattering, I will use the Kratky plot on the right-hand side figure, where you can see in green the scattering of an isotropic chain, which has two parts. At low Q, you see a parabola increasing curve, which corresponds to the Grignon plateau for S1 of Q times Q squared. Meanwhile, at large Q, you see a plateau because you have the multiplication of Q squared by the 1 over Q squared decay of the scattering of the Gaussian chain with a fractal dimension 2. So now for those who know about polymer dynamics, going into more detail, we can follow the relaxation after stretching, and if we can use the Rouse model at short time, and in this case the melt is equivalent to a rubber of mesh size equal to the Rouse blob, which varies at T at the power 1 over 4, which has a consequence the fact that we have the same curves as shown before with a crossover QC, which varies as T at the power minus 1 over 4. Now, those who know polymerology also know that eventually, at large relaxation time for long chains, the Rouse model is replaced by the reptation model, in which, as you can see in the sketch above, the chain remains trapped in a tube due to the other chains in its middle. So the intensity at large Q is an average of an isotropic scattering and isotropic scattering, as you can see in the formula. And finally, the scattering, which you can see in this Kratky plot, rejoins the isotropic scattering with a single crossover in Q. QC is here equal to the inverse of the tube diameter. So here is the experimental results. Small angle neutron scattering allowed us to measure the form factor from a mixture of normal and deuterated chains, so a melt, under relaxation after stretching, and one can see that the results agree with the former description. I will not go into more detail. Let us now consider a solution of chains. When you increase progressively the concentration, at first the intensity increases. At a certain point, there is what is called overlapping. That means there is no more volume for more chains. Then, if you want to add more chains, what you observe is that each chain subdivides itself in smaller entities, which are called blobs. Now, the scattering of this semi-dilute solution is represented in red on the right-hand side figures in log I versus log Q. If we consider a more dilute system, Xi is larger, as we just saw, so that the 0Q limit of the intensity becomes larger. And so you can see on the left figure that this is equivalent to say that when you dilute, when you add solvent, the intensity is actually increasing, which is a bit counterintuitive. So if we now were imagining that we stretch the solution, the semi-dilute solution, we would observe that Xa increases along the stretch direction and the intensity also increases along this stretch direction. So here the master word is disinterpenetration. When you dilute or when you stretch, the chains are disinterpenetrated. They will occupy more volume and the scattering will be larger because the correlation length is larger. I agree, it seems a bit weird to consider stretching of a solution since solutions are flowing, but we can consider the case of shearing effects in this very viscous medium. Anyhow, we will now consider the case of gels which are elastic and which can be considered as some kind of cross-linked semi-dilute solution. This slide summarizes a huge amount of work on network heterogeneities. On the right hand side, you can see that you can get heterogeneities even if you are not expecting them. You can get heterogeneities from copolymerization of monomer and crosslinks, from statistical crosslinking of very long chain in the middle, or on the bottom, or from unlinked system. So on the left-hand side, you see the names of the authors of different models, and on the middle you see the prediction for the scattering, which in some case is directly showing some heterogeneities with some low Q overscattering, and in some other case, like in the Bastide-Leibler model, these heterogeneities are hidden just after preparation. On this figure, we have represented on the left-hand side, on the bottom, the heterogeneities as more concentration region, which produce some oscillation, some variation, spatial variation of a concentration as a function of a distance, as represented on the turquoise curve on the top. Of course, this is at the moment gel before stretching, so the scattering is isotropic. So now we stretch the gel, that means we take it, we take the two ends of the gel within some clamps and we pull. And what will be the scattering in this case? Well, if the heterogeneities are at first interpenetrated completely or at least partly, they will be disinterpenetrated by the stretching, as you can see here. This will be increasing the spatial variation of the concentration, and the scattering will be larger in parallel direction, while it will be lower in the perpendicular one. So one can remark here that stretching is equivalent to swelling, but at the same concentration. So you gain in correlation length, but you don't lose in concentration. So the intensity along the stretching direction increases more strongly than for dilution. And now the final aspect of the scattering is represented on the right-hand side. And you can see a rather weird figure, which is due to the fact that the 0Q limit in parallel direction is higher than the 0Q limit in perpendicular direction. This is different from the scattering of a deformed single object, in which the 0Q limit is the same in the two directions. So because the because the intensity along parallel direction is larger, some tranches of intensity are seen only along some direction which are close to the parallel one and are not seen along direction which are close to the perpendicular one. This is the origin of this strange shape called the butterfly shape. Well, now I show you some results from small angle neutron scattering, which actually correspond to a vicinal case to the one of a gel swollen by a solvent. It is a gel swollen by some small deuterated chains inside a network of non-deuterated chain. So owing to the contrast, you get the butterfly figure on the right-hand side above. Meanwhile, on the left-hand side, on the bottom, you see the scattering in the perpendicular direction, which is not affected very much by the deformation, probably because the heterogeneities cannot interpenetrate more than they are. Meanwhile, on the top of the figure, you see the parallel scattering, which shows a progressive disinterpenetration of the heterogeneities when lambda is increasing. So in most of the case for networks, you have this disinterpenetration effect of heterogeneities, which leads to the butterfly oriented as you saw before. However, to end this story, I will show you a case where we have normal butterflies, normal in the sense of onuki, which were produced by a gel made of sliding rings, so no real heterogeneity and no freezing of these heterogeneities. And in this case, Shibayama showed that you have a butterfly in the opposite direction. That means in this case, the signal is decreasing along the stretching direction as for a single object. Now I want to tell you about a more heterogeneous system, nanocomposite. I will define what it is just after. And this work was done with people of LLB in Saclay, Jacques Gestin, Fabrice Cousin, and thesis student, and people from chemistry laboratories, in particular the lab of Marseille with Didier Guigmes and Denis Bertin. So how can we get polymer nanocomposites? There are actually many ways, you probably know. I will show you here a very simple way in which you mix some nanoparticles, silica nanoparticle, and polystyrene chains, which are dispersed in the same solvent, dimethylacetamide, which are then evaporated very slowly, and at the end you get a film with nanoparticles which are more or less dispersed inside the polymer. How well are the nanoparticles dispersed in the polymer? This is actually the main question. You can see here two examples. On the left-hand side, you have a low concentration of nanoparticle, 5% in volume, and you can see that the nanoparticles are organized in small aggregates which are far from each other. Meanwhile, when you increase the concentration of nanoparticle up to 15%, you see that the system is much more crowded, and then now visually you can see that all the aggregates are connected together. Maybe you were surprised, but this is the first time I show you something else than some scattering curves. Actually, these are electronic microscopy by transmission pictures, and I can also show you the corresponding small angle X-ray scattering because there is a contrast between the nanoparticles and the polymer, and it is possible to modelize the curve, which are here, the modelization is here drawn in blue, to account for the different level of organization of these nanoparticles. Well, I hope you were not disturbed by some kind of cooking noises behind my voice. So now, what is the effect of stretching on this material? Well, I first consider the simplest case. I've drawn the three nanoparticles, and you see that when you stretch the material, imagine the particle is not deformable, so it remains a sphere, but the interparticle distances are deformed. This actually corresponds to a kind of minor disinterpenetration. So there should be some effect even if a nanoparticle are separated. But if are now aggregated, there should be stronger disinterpenetration effect because you would have some kind of heterogeneities which are of the same kind of the one which we saw disinterpenetrated in some polymer network. Indeed, this is what you see here. You see a very beautiful butterfly with two lobes, which is obtained when you have a moderate deformation of this nanocomposite. Now, if you stretch harder, more, then you get 4 lobes here, a 4 lobes butterfly pattern on the left-hand side on the bottom, and this is probably due to an additional effect which I will explain on the next slide. Indeed, as you show on the bottom of this slide, actually the transverse shrinking of the sample makes the hard zone closer together along the transverse direction, so that when you displace all of these aggregates, they are to avoid each other, which creates some local shear and some local reorientation, and this results into this 4 lobes figure, which has been simulated at first by us with Julien Aubertisseur and Yaya Rabi, and later on people from Japan made much more evolved simulation of these different effects. Now, instead of just looking at some shapes of iso-intensity curve, we can look along a given direction at the scattering or even at the structure factor. That means the result of dividing the scattering by the form factor of a nanoparticle, which we know. So you see on the left, in the perpendicular direction at the top, that there is not much evolution in this first example when you deform more and more. The structure factor remains very close. Along the parallel direction on the bottom, you see that the scattering curves, or at least the structure factor curves, are shifted to the left. That means that the distances are increased, and but this doesn't correspond to a fully affine deformation. On the right, you can see an electronic microscopy of a sample which has been stretched and then cut to do the electronic microscopy observation, and you can see clearly that the different aggregates have been oriented by the stretching along the stretching direction. If now we use much higher concentration of nanoparticle, 20%, we see that the structure factor is now strongly shifted along the Q direction. In parallel direction, it is shifted along smaller values of Q, which means larger distances. And in the perpendicular direction on the bottom, it is shifted in the direction of larger value of Q, that means smaller distances. In all cases, the butterfly shapes are strongly deformed, so that we have an important influence of the deformation here. And what is interesting is that this second case correspond to a much stronger dependence of the stress with elongation ratio, as you can see on the right-hand side figure of the mechanical stress-strain curve. Well, I want to terminate this description of butterfly pattern behavior by following these evolutions along the curve of stress versus strain. Let's take the curve of cycle 1, which is red. You see that when we first deform the material, there is a very steep increase, and then the stress evolves much more slowly. And during all this variation, you observe the butterflies for lambda equal 1.5, 2, and 3, which have a classical shape. Then we stop deforming and we let the sample return to the isotropic state, so to recover its deformation. And we obtain, when this deformation is recovered because the sample is elastic, we obtain an inverse butterfly instead of the isotropic scattering which we had when the sample had not been deformed at all. Moreover, when now we want to re-stretch the sample, we observe a much smoother stress-strain curve. We do not observe anymore the steep part at the beginning, and if we recover again the deformation back to zero deformation, and that we apply a third cycle, this third cycle is now very close to the second cycle, so that what turns out here is that at the first cycle we have actually deformed the network of the nanoparticles, and we have actually more or less broken this network, these filler networks, as you can see by the fact that we do not have this increase again at the second cycle and at the third cycle. Now the last section of this talk will concern not the NPs but the chain. Actually, a way to hide the nanoparticles in the sample and see only the chains is to use sophisticated zero average contrast method. We synthesize a copolymer made of H normal monomer and D deuterated monomers, which in average has the same scattering length density than the silica. So the silica are hidden. Moreover, we add to this mixture some normal chains and some deuterated chains of same molecular weight, and by symmetry, the only remaining term in the scattering is the form factor of the chain. First immediate benefit of this approach is the form factor in the undeformed state at rest. We have observed that in many different cases, different polymers and different kind of fillers, that this form factor is the same as in absence of nanoparticles. In other words, there is no effect of confinement or no other effect of nanoparticles on the isotropic conformation of the polymer. So now to see the stretch conformation in the deformed nanocomposites, we proceed as many other times before. We make a film, we stretch the film at a temperature larger than the glass transition temperature so that it is soft. we apply a certain gradient and a certain stretching ratio, and we can observe now directly the form factor. Of course, this is a lot of work, but the result worth the trouble. It is really impressive, as shown on this figure, for a molecular weight of 315,000 Dalton. Let us first look at the two top figures for lambda equal 2 and lambda equal 4. You can look at the curve in red first, the red point, which corresponds to 0% silica, and then you can look at the blue points, which correspond to 5% in volume of silica, and you can see that they superimpose on each other, so that the form factor is the same. You can also look on the third figure on the bottom, the same effect at a very large lambda of 6, deformation ratio 6. So in all these cases, you see that the stretch deformation is the same without and with a nanoparticle at least at 5% in volume. We can also look at a larger volume fraction, this time 15% in volume of silica. And in this case, the film is very rigid, so it's difficult to stretch at large lambda without breaking the sample. So we stretch only at lambda equal 1.28. And you can see on these on the figure, so on the right hand side at the bottom, you can see that again there is a superposition of the red point for 0% silica and the blue point for 15% silica in volume. So here again, the conformation of the chain is the same with and without the silica. This is quite striking if we compare with the level of stress for the two materials, the 0% one and the 15% one at this lambda equal 1.28. You see on the left-hand side figure the two red points, and you see that the ratio between the two values of stress is more than 10. Meanwhile, the conformation is the same. So the reinforcement doesn't come directly only from the chains. If we pay more attention to the stress curve on the left-hand side figure, we see that all of them look as vertically shifted compared to the one at 0% deformation, except the last one at 15%, which first shows a kind of overshoot. But altogether, there is this vertical shift, so that we can imagine, like I draw on the top right, that you have two contributions, one of the chains on the right, slowly climbing, and one from the fillers on the left, which correspond to a very sudden shift. To better understand the origin of the reinforcement, which is obviously due to the fillers only, we had the idea to subtract the chain contribution at 0% silica fraction from all the different curves. Very easily seen on the left-hand side figure. You see that now we have a filler contribution, which is more or less a plateau, except the overshoot for 15%. This overshoot is actually due to a kind of softening under strain of the very rigid sample. So altogether, we have a plateau contribution from the silica network. So we can imagine a model with two contributions acting in parallel, the one of entangled chain on the right in red and purple from the entanglement contribution, and a constant contribution here in blue, analogous to a dry fraction on the left, which comes from the filler. This is actually the one we identified before when we compared the first and second and third deformation cycles. And we attributed it at this time to a progressive breaking of a filler network, which one can also call reorganization. Time is passing, but I cannot refrain from showing you the effect of a relaxation on the chain, a relaxation after stretching. That means we keep the film hold at constant length. You see that the stress is decreasing progressively with time. We wait until 24 hours, and you see that the final result of the deformation and relaxation on the chain conformation is the isotropy on the bottom for the 0% silica fraction, but also on the top for the 5% silica fraction. There is actually a bit of strange shape there, so it's not perfectly relaxed, but it's very close to be relaxed. Actually, up to now, we have been very lucky in our synthesis of nanocomposites because we just mixed the nanoparticles with the polymer without any other chemical preparation, except that we used the right solvent and the right method of drying. But to complete this nanocomposite description, I will cite another way of synthesizing a nanocomposite system which open, I would say, more possibilities. It is using grafting, which has been done in collaboration with chemists of crops in Marseille. We use an industrial initiator from Arkema, and we attach to it silane, and then we can attach the initiator to the silica particle of 10 nanometer. The conversion is very good, 50%. We have about 500 chains per particle with, for each of them, a molecular weight of 30,000 Dalton. To make the nanocomposite from the nanoparticles and the polymer, we proceed right the same as for the non-grafted particle. We disperse them in the same dimethylacetamide solvent, mix with a solution in the same solvent of the polymer, and evaporate for 80 days. We take care of removing as much solvent as we can. Grafted nanoparticles, through a vast study, we could obtain all sizes of aggregates from several tenths of microns, as shown on the TEM micrography at the bottom of the slide, to individually dispersed particles, as shown on the TEM microscopy at the top of the three TEM figures. The driving parameter to go through all this series of different type of dispersion is the ratio of the mass of the grafted chains over the mass of the matrix. As predicted by Dejean, when this ratio is large, the small matrix chains swell the grafted brush and the nanoparticles repel each other so that the dispersion remains individual. And when R is small, then the brush are not swollen by the matrix chain because they cannot enter. They remain dry, and so they do not repel, and you get these very big lumps which you see at the bottom. In the middle of the three micrographies, you see behavior which is very close to the one on the left hand side, which is the one for non-grafted silica. What I want to show you here is how to use the system where the grafted nanoparticles are individually dispersed to follow the deformation of the grafted corona. We are using the same HD statistical copolymer which is matching the silica scattering length density. So the matrix here is matching the core of the nanoparticle, and we see only the coronas, which are made out of normal polystyrene, which have a contrast with respect to the HD statistical copolymer. So if now we stretch the film we have made, you see the different scattering patterns on the right-hand side figure. You see the variation along the horizontal axis as a function of increasing the silica fraction, so the intensity is stronger and stronger, and you see its variation with the elongational ratio on the vertical axis, and you see that the anisotropy of these patterns are increasing. Note that all these patterns are still of the butterfly shape type, which means that we have still not only some scattering from the intra form factor of the corona, but also some scattering due to the inter-corona structure factor. The good news are that we can get rid of this inter-corona scattering by doing the same experiment on the same sample using X-ray scattering, because the X-ray radiation is sensitive only to the contrast between the silica and the polymer, whatever it is, the HD polystyrene matrix or the H polystyrene grafted corona. You see on the left-hand side the different figures, which show some strikingly marked anisotropic patterns. And what we will do is that we will divide the patterns on the right-hand side by the corresponding pattern on the left-hand side, so that we will get rid of the structure factor and obtain only the form factor. Before to give you the result about this division, I wanted to dwell a little on a specific comparison between electronic microscopy and X-ray scattering. You see on the left the X-ray scattering patterns, which show some oscillation perpendicular to the elongation line. Meanwhile, when you look at the electronic microscopy, you don't see a lot of specific organization. We have marked by some arrows which are in dotted lines the direction of the elongation. You see that the particle looks a bit like a line along this, making some kind of rows along this direction, but it's very difficult to see some specific distances. So this shows how much more sensitive is the scattering than the microscopy. So now I return to the result of this division. More precisely, what we do is we first divide the results which are on the left-hand side by the silica form factor, which we know. So we get the structure factor of the silica cores, which have the same centers than the corona. So we have the right to now divide the signal from the corona by this structure factor and get the form factor of the corona. Two examples are shown in this slide for the maximum silica fraction of 14%. On the left-hand side, you see an example for intermediate elongation ratio of lambda equal 1.5. You see that the form factor along the two direction parallel and perpendicular in log-log plot is strongly different. So we have a shift of the parallel scattering towards lower Q, that means larger distance. In other words, the corona is strongly deformed when the sample, when the film is deformed. You see the same thing on the right hand side for a larger lambda, lambda equal 4, for which actually the shift between the two curves is not so strong, which could be explained by the fact that this the corona is actually not so much deformable, since it makes only a thin layer around the core, the silica core, which is undeformable. So when it is strongly stretched, as for lambda equal 4, the corona makes a very narrow, very thin films around the silica core along the perpendicular direction, and this film may be less deformable. Anyhow, what we can conclude of this measurement is that the corona is very deformable. So, in particular, it is not glassy as was proposed by some researcher. Indeed, the existence of glassy bridges of polymer between two aggregates of a nanoparticle would have explained the strong reinforcement, because it would enhance the connectivity between the aggregates, so make some large distance connectivity, and also the rigidity, since this connectivity would have been rather rigid due to the glassy state. So this is not observed in our nanocomposites, although a rather strong mechanical measurement has been obtained for this composite. We could then believe that in very aggregated case, where the nanoparticles are very close to each other, this glassy layer would be more efficient. The answer from this electronic micrography is no. You see in this deformed film that the big aggregates are actually very highly deformable, so that you can imagine that the polymer which is inside the particle in the aggregate is highly deformable. So it's now time to say goodbye. Without too much math and being a little sloppy sometimes, I discuss the deformation of single objects, especially when it is similar at all Q's, which is called fineness, or when you have a loss of a fineness when you go to larger Q, for chains in rubber or in polymer under reptation. I have discussed the inter-object correlation, the disinpenetration effect associated to stretching, which inverts the relation between the parallel and the perpendicular direction, the parallel becoming larger at low Q. I discussed the butterfly shapes in gels, revealing cross-link intensity heterogeneities in nanocomposite, where I discuss the reorganization of a filler together with reinforcement effects, and the deformation of chains and of the corona of a nanoparticle in the case of grafting. So maybe you can guess there is a lot more which I could have presented. For example, I just show you a last electronic microscopy picture of magnetic nanorod, and I let you guess what would be the scattering. And I thank you for listening. Thank you. Bye-bye.